In this video, we are going to be looking at how to find the maximum and minimum values of a function. This is a process called optimizing, and later, once we get this skill down, we're going to be looking at some application problems where we use this to, say, maximize the profit or maximize the revenue or minimize the average cost. So this first video mostly is going to be about learning some terminology. This is a lot of what this is, but we're also going to find some relative and absolute maximum and minimum values and learn about the Extreme Value Theorem. Okay, so here's a list of our new terms. First of all, we have this term extrema. So this is just the term that we use to indicate the collection of maximums and minimums of a function, so the high spots or the low spots of a function. And then we have four basic types here. We've got a relative maximum, we have a relative minimum, we have an absolute maximum, and an absolute minimum. And the idea here is, suppose we have a function that maybe looks like this, and it stops there and it stops here. We can tell that right about here our function has a high spot. We have a high on our function, and that's the maximum value near that spot. But over here I can see that, okay, I have a larger y value. So this spot over here, this would be the absolute maximum. And this spot here would be a relative minimum. I'm sorry, a relative maximum. Because near this spot, this is the highest y value, and this is the highest y value overall. And then we have the same thing for minimums. So this value right here, this is our low spot on our function. This is a minimum value, but it's not the lowest y value overall, so it's just a relative min. And then over here, this is our lowest y value overall, so that would be our absolute minimum. Let's look at a graph where we have lots of these types of points. So we've got a graph that is defined over a bounded interval. So we have this word bounded interval, and our domain for our function goes from -11 up to 15. So this is a bounded interval because it doesn't head off towards infinity in either direction. We are supposed to figure out where our function has relative maxima, relative minima, absolute maximum, and an absolute minimum. So let's just go through our function from left to right and figure out what we've got going on here. So let's start with this first point that I have labeled here, -11, -6. If I look at this, this looks like a low of our function because it's a low spot. And if I compare it to the rest of my y values on my function, this is the lowest y value that my function achieves on this interval. So this is our absolute minimum. So our absolute minimum is going to be -11, -6. Okay, moving to the right, our next spot is this spot right here, -6, +6, and this looks like a high spot on our function. And if we compare it to the rest of our y values here, this actually looks like it's the highest y value. So this is our absolute maximum. So that we have -6, +6. Okay, moving to this next point. So I'm looking at this point right now. So this looks like a low because we're at a low spot on our function. So it's going to be a minimum, and I can tell that it's not the lowest overall because this one's lower over here. This point that's circled in red is lower over here. So this is going to be a relative minimum. So -2, -4 is a relative minimum. Okay, so let's keep moving to the right here. So we have this spot right here. We have 3, 4. This looks like a high spot, and our function does go higher than this, so it's not our absolute high spot, but it is a high spot, so it's a relative max. So we have 3, 4 as a relative max. Continuing to the right, we have this point 7, -5. This is a low spot, but again we have a lower y value, so it's not our absolute minimum, but it is a minimum, so we're going to add this to our relative min list. And then continuing to the right still, I'm going to look at one more point here. Let's label this point right here. So this is the point 12, 0. Now, this is kind of an interesting point. This is not a high spot or a low spot because our function just kind of pauses here and then it continues up. So this is not a high, it's not a low, it's nothing. But over here, this spot right here, this is another high spot on our function, so that is another relative max. Now, I'm going to scroll down here. These spots can be categorized into 3 different types of points. We've got 2 points that are endpoints of our domain. Okay, so they could be endpoints. Another thing that we've got going on is we've got 3 points here where our tangent line is horizontal. So these 3 spots here have a horizontal tangent line. So that is this first type of point. And then we've got one last point, this point right here. This point has a sharp point on it, so our derivative is actually not defined there. So these maximums and minimums tend to occur at 3 different types of points. Places where the derivative is 0, and we call these stationary points. Places where the derivative isn't defined, like where you have sharp points or vertical tangents, those are singular points, and then the endpoints of the domain. Okay, so let's look at this extreme value theorem. It says that if f of x is continuous on a closed interval a, b, then it will have an absolute maximum and an absolute minimum on that interval. Each absolute extremum must occur at an endpoint, a stationary point, or a singular point. So there's a couple things that I want to talk about here. First, let's talk about this word continuous. That is just a mathematical term that means that the function can be drawn without lifting your pencil. That's a really basic way to say it. So function can be drawn without lifting pencil. So I'll draw a couple of examples here in a second. But we have this other condition here. It says on a closed interval a, b. Okay, so the one that we just were looking at, we were looking at this interval -11 to 15. This is an example of a closed interval. If I took one of those endpoints out, so I don't include -11, then this is not a closed interval. Or if, say, one of the endpoints goes off towards infinity, this is another example of something that's not closed. Okay, so we have a function that is continuous and closed on this interval. Then our function will have a maximum and a minimum, an absolute max and a min on that interval, and we saw that in the last example. Remember how we had an absolute max and an absolute min? And these mins and maxes will occur at endpoints, stationary points, or singular points. And we saw that those are the 3 types of situations that we had in that last example. Okay, so let's look just a little bit more closely at that word continuous. So this is an example of a continuous function. My function can be drawn without lifting my pencil. Here's an example of something that's not. So this is yes. Maybe our function does something like this. So it is not continuous here where I have this vertical asymptote because it zooms off towards infinity there. Here's another example of something that's not continuous. So here we have a big break in our function. And so as long as we have a nice continuous function, then we can be assured that the maximum is going to occur at the endpoint, stationary point, or singular points, and there actually will be a max and a min. But if we have anything funny going on where our function is not continuous, then we cannot be assured that we have that max or a min, and we also can't be assured that the max and the min occurs at the endpoints, or the stationary points, or the singular points. Okay, so let's look at another example. Notice at the top it says this is an unbounded interval, and if we look at our domain here, see how I have arrows here and an arrow here? That means our domain goes from negative infinity up to infinity. Our function is defined for all x values, so clearly this would not be a bounded interval because it extends towards infinity in either direction. And I have my points labeled here, some important points. One thing I do want to point out is I was intending when I drew this example that our function is kind of displaying some asymptotic behavior here. So as x gets really big, so as x tends toward infinity, our y values here are getting close to 0. Okay, so last time we just went along our curve and wrote down our points that way. This time, I want to do it slightly different. What I want to do is I want to list all my stationary points. So stationary points, remember, are where your derivative is 0, or where you have a horizontal tangent. So if I look at my points here, I have a horizontal tangent at this point, so I have -7, -5. I have a horizontal tangent at this point, so I have -2.5, 2, and I have a horizontal tangent at this point, 7.5, 5. Then let's find our singular points. Remember, this is where your derivative is undefined. So either we have a vertical tangent or we have a sharp point. So this point right here, this 2, -3, that is our only singular point. So this is 2, -3. And then in this example, remember, we don't have any endpoints because our domain goes from negative infinity to positive infinity, so we have no endpoints. Okay, so we've found our stationary points, our singular points. Let's classify these. So let's start with this one. That one looks like it's a low. So we are thinking, okay, that's going to be some sort of minimum. And if I compare it to the other y values that I have here, it looks like it's the lowest y value that my function reaches. So it continues up forever that way. These y values are bigger. And then it looks like over here that my function is supposed to be, getting close to 0 but never reaching it. So this is going to be our absolute min. So let's look at this next one, -2.52. Here, this looks like a high spot on our function, but clearly I have other higher y values. So this is a maximum, but it is only a relative max. Next, let's look at this one. So this is another high spot. So the question is this an absolute max or is it a relative max? And look at this arrow over here. So this means that my function is continuing up this way. So there are lots of higher y values over here. So this is only a relative max, not an absolute max. Okay, and then finally, our singular point, that's a low spot, and it is a relative min. When we are doing these problems, you're going to have this same method here that we did sort of on the last problem. When we need to find the maxima and minimum of a problem, of a function, what we're going to do is first we're going to find all those stationary points. So we're going to figure out where does our derivative equal 0. Then we're going to find all the singular points. These are the places where our derivative isn't defined, and we're going to look for zeros in the denominator. So maybe our derivative function looks like f prime of x is 2 over 3 times the cube root of x plus 1. So we would not want there to be a 0 in the denominator there, so x equals -1 would be a value where our derivative function is not defined. So that would be an example of what you're going to see for singular points. Then we're going to look at our endpoints. These are always given to you. And then finally, once I've got all 3 of my types of points where I'm going to have my mins or maxes, I'm going to classify each of them. So it could be a relative max, it could be an absolute max, a relative min, an absolute min, or maybe it's none of those. For instance, that first function that we looked at had a spot where it did this, right? Where it leveled out there. So here I have a horizontal tangent. So it would look like a stationary point, but if you look at our function here, it is not a max and it is not a min. So look for the next video where we go through this process with an actual function instead of just a graph of a function.